Okay, good morning. We have today the second Data Cellar webinar, Decision Support System and Data-Driven Services and Artificial Intelligence Libraries. We are happy to have you with us. Let us give a couple of minutes for people to connect, and then we will proceed with our planned presentations. So thank you very much again, and wait a couple of minutes and we'll start. Okay, I think we have given enough time for people to connect. Thank you very much again for waiting. We are today for our second webinar of Data Cellar. We want to give you the progress that we have achieved through the project. And we would like today to present to you the decision support system and data-driven services of artificial intelligence libraries. It is our full agenda for today presented here. And after my initial opening remarks, we will have our colleagues Luis Luengo and Yanis Iagovidis to present to us the decision support systems and digital twins. And following them, we will have the opportunity for your questions to be heard, that you can use the procedure that Aranza is giving you through the chat to set out your questions that will be addressed by our colleagues. Then, after this theme, we will move on to artificial intelligence services for local energy communities that will be presented by Sara De Luca. And then finally, we will have, after Sara, of course, we will have again some questions to follow. And completing this session, we will have our coordinator, Martina Galluccio, that will give us some main takeaways and conclusions for today's event. We are here with you with Data Cellar, trying to respond and show the evidence that we are trying to meet the strategic objectives of Europe, of EU. So we know that data is increasing exponentially, and we have relevance to data that is recorded in 2018 as being of 33 zettabytes, a very big number. And by 2025, this big number is going to grow substantially to 181 zettabytes. And as Data Spaces Association, International Data Space Association indicates, most of this data is not available to be used usefully around by applications, etc. So 80% of that is not used. So the European Commission has put a strategy forward and is aiming to achieve a single market for data that will foster Europe's global competitiveness using this data and facilitating the economic growth of Europe. Of course, this requires investments, and by 2027, EU expects to spend about 2 billion euros to support this process. Of course, it's fully aligned with Green Deal and Fit for 55 objectives and the green transition, something that we are a bit proud within Data Cellar is that we are following this strategy and we are trying to reach a common European data space, a single market, data that can flow within EU and across sectors. That's very important. And availability of high quality data to create and innovate. European rules must be mandatorily be respected, and is something that we take great care within Data Cellar. Rules for access and use of data are fair, practical, and clear, and certainly we have a very strict governance around it and how mechanisms are used in order to make it useful and usable. So this is as my introductory points are, and we can move with the first theme of today, which is decision support systems and digital twins. And please, Aranxa, give access to our colleagues to proceed, which is Luis Luengo that will start the presentation, and followed by Yanis Iacovidis. And as I said before, prepare your questions, follow closely, and prepare your questions to allow them to proceed. And obviously, we would like to have some discussion and presentation within this seminar, because we would like to hear your opinion on this, about what we are delivering through Data Cellar. Thank you.
Okay, Venizelos, thank you for the introduction. So my name is Luis Luengo. I work for CIRCE in Spain. Can you please confirm that you can see the full screen? We can move this around here. Can you see the full presentation?
Yes, we can see full presentation.
Okay, great, thank you. So Venizelos explained a little bit the idea of the Data Cellar project. Most of the people that joined today are aware of it. But today we are focusing, or at least in my presentation, we are focusing in some of the tools that we have prepared in how we can use all this information. Especially, we are going to talk about energy, because we have identified that a lot of data is related with energy, for example, the energy meters or consumption data, generation data, and a lot of different kind of data that can help the users to take better decisions on their energy consumption. Okay, so the question is, why does anybody need a decision support system? Okay, I can manage my energy. I know more or less when the energy is cheaper or more expensive. So why do I need that? The point is, there is a lot of information which is available, but as Venizelos said, we are not able to use all this information. We know we have some PV power that is produced over the day. We know that the price of the electricity is changing every hour, but even though we are not taking action on it. So these kind of tools or energy systems can help to take better decisions related on how we consume our energy. By using simple strategies, like for example, sizing accordingly a PV system or a battery system can help to increase our self-consumption, which is the energy that we produce and that we consume, and also to reduce our energy costs. So at the end, what we are seeking for here is to have some optimal grid operation, which is also a tool for DSOs. It's not only we are not only focusing on energy consumers, but also distribution system operators that can use these algorithms in order to identify where they can have problems in their grids, and then place different assets like batteries to avoid these problems and to defer investments. Okay, so at the end, what we want to do is to close the gap between the tool developers and the energy end users and DSOs. So here we are going to present the 5 functionalities we have developed. This has been a jointly work between Circe and Third. My colleague Yanis will be presenting the last functionality at the end of the presentation. And we are presenting before everything the digital twin, which is the tool that allows us to make grid calculations if the user doesn't have this grid model. Okay, so at the end of the day, we want to study a lot of grid systems, grid networks, but sometimes there is no possibility to obtain this information. Okay, so what we propose here by doing this digital twin is to create a grid model out of really small information, which is mainly the points of the consumption and the voltage. And with this, we are able to build this grid model, and we can perform a wide range of simulation. Okay, so at the end of the day, we are hoping to help with investment planning, the status estimator, and to identify if there are any kind of non-technical losses. Okay, so the digital twin, what we are doing is to creating this grid model out of only power and voltage measurements related to different energy meters. So we can build the different lines from what you see here in the picture. All these arrows are the different consumers with these P and power and voltage measurements, and we identify that we have a source. Okay, but we don't know what is in between. So we don't know if there is a kind of problem in here, and we cannot run simulations. So, for example, if we would like to place a new PV system in this point, we don't know how this whole grid will be affected. Okay, so by using this, we can build a number of feeders that hang from the secondary substation. In this case, we call it source. And we are able to perform the different further calculations that we are going to explain afterwards related to grid operation. This is suitable for low voltage and medium voltage levels since we are using a radial topology. Okay, so maybe this picture helps everybody to understand how the digital twin works. Okay, right now, this is what we have. We have some secondary substation here, some electrical devices. We have some feeders that bring electricity to the homes, and we have all the meters from the different consumers. Okay, we have this information, but we don't know what happens in here. Okay, because this might be a really small grid, or it can be a small village, and we don't have this kind of information since there is no records, or the distribution company didn't facilitate this information. Okay, so what can we do? We can use this digital twin in order to build up all these different cables and lines to connect with the secondary substation. So we can identify what happens in all these different lines and to see if there is any kind of problem and study new situations. At the end of the day, since this one, since we are building lines, and you can see this is a really primitive schema from a grid, this is a first approach, but then we are able to identify the different grids according to the different points that we are studying. Okay, this is an example of one of our validation cases that gave us these consuming points, and we were able to build the different grids that are present in the system. Of course, we are using really small quantity of information, and sometimes the lines are not perfect. Okay, I agree with you that this line that crosses this other line might not be 100% correct, but it gives us an idea with the small amount of information that we have at the very beginning. It's also important that we are able to build these lines and to move them to another location, because here in Data Cellar, it's very important to the confidentiality of the data is very important. Okay, so a lot of validation cases were happy to give us information about the lines, but they want to have some privacy, and this is the reason why we anonymize the location of the different lines. Okay, so this is for the digital twin, which we will come back afterwards for the tools related to grid operation. But now we are going to start with the two tools that are directly used for end consumers. Okay, first of all, we have the optimal resizing, which is a tool that allows us to calculate the best combination of PV and battery system that has the lowest levelized cost of the energy. So the amount of money that we are paying for the energy in the whole lifetime of the project, and we are based in load consumption, solar resource and battery capacity, and also the energy prices. We are also considering the possibility to buy energy from the grid and sell energy to the grid whenever we have an excess of energy. We can choose from different scenarios. For example, we can have a PV installed on a rooftop, or we can have an energy community having a PV installed on a field with battery capacity, and there is no problem to study different systems. We understand that each consumer or each energy community has different necessities, and we wanted to cover the whole possibilities. And also, very important, we are doing the calculations. We are performing energy flow calculations on an hourly basis. This means that we are not just taking the amount of energy produced with a PV system over a year, let's say 100, and I'm consuming 100 kilowatt hour in the whole year, so I'm perfectly consuming everything. No, it's not like this. And we are considering every hour what's happening every hour, because as you may know, we can produce a lot of energy, but if we are not at home when we are producing this energy, we cannot consume it. Okay, so we are not using aggregate data, but hourly data. Then we are doing a profitability analysis, and we are optimizing the calculations by using a lot of iterations by using genetic algorithms. Here you can see the flow diagram of the algorithm. Okay, we have an energy management system, and we have all these kind of iterations based on genetic algorithms. In case you want to have more information about this, we have a paper that has been published. We have here the link. I don't know if we will be able to share the presentation afterwards, but you can have a look on how this was performed. Okay, and now we are going to do a small live demo. Hopefully this will work, in order that you can see how this works. Okay, what you can see here is a is our user interface that I developed myself, so it's very ugly. We all agree with this, but just keep in mind that everything will be integrated in a dashboard. For the time being, we are working on this, so we are going to use this Excel file. Okay. So let's make an example. Okay, you can see here that we can introduce the location of the energy community. Let's take this one, for example. And here we can introduce the amount of load consumption that we have. We can introduce either a year hourly profile, a day hourly profile, some contracted power when we will select if we are a household or a business, and then we can enter here the amount of power. We can also go for average consumption, and we will introduce here the average consumption. For the time being, we are going to use a yearly hourly profile that we will upload afterwards in here. We have already introduced the load consumption. Now we are going to introduce the electricity price. We can also say yearly profile, daily profile, or fixed price. Let's make an example here, very optimistic. Okay, let's say that we are buying energy very expensive, and we don't get so much money from our energy. So this will, at the end, will maximize our PV system. Okay. Let's say also that we cannot sell PV excess energy to the grid, but we have a battery, and we are also able to charge this battery from the grid. Okay. So from this point, we are just selecting our preloaded Excel file. I'm aware this doesn't look so nice, but at the end of the day, we will have a nice user interface integrated in a dashboard. And then we just check that all the values are correct. Okay, everything is correct. We will wait 5 minutes, and then a window will pop up automatically to show the results. Okay, so let's launch the simulation, and then just let me continue with the presentation till we have the results. Okay, what we are going to see is this screen. We have a lot of things here. Okay. And we have 4 boxes. In these 4 boxes, we have the optimal configuration of the system, where we have some installed PV power, the battery capacity, the battery power, because the inverter of the battery might not be at the same level of the capacity. And in case we allow to sell and buy energy to the grid, the prices, the recommendation prices we should use to do it. We also have some energy results, which are the self-consumption and the self-sufficiency ratios, which give us an idea on how independent we are from the grid. We have also some economic results that can help us to understand the profitability of the system. This might help us also to go to a bank and ask for a loan and say we will have these figures, so I will have the money back in 2, 3, 4 years, I don't know. So it's easier to sell this to a bank. And then we have this more technical KPI, which is the levelized cost of the energy of the current situation. So right now, before installing this PV and these batteries, and the price that we will have if we install these systems. Okay, so in this case, you can see there is a huge difference. We have schematically the different energy flows that we have between the grid, the battery, the PV, and the loads. And here also in the right-hand side, you can see a Sankey diagram that is very visual, that says what is the energy doing. So in this case, we see that we have a lot of energy that is being produced, that is being fed to the grid, and a small amount is directly to the load, but some of this energy from the PV is going through the battery. So this also gives us an idea visually on how the energy is performing. Okay. So I will continue with the second functionality. At some point, first functionality will pop up, so I will come back shortly to the results. But let's continue with the flexibility estimation functionality. And here, we are not caring about sizing, but we are caring about operation. Okay, we understand that we have already a system, let's say a household with a PV or not, with batteries or not, and with some dispatchable assets that I can control, and then I can be a little bit proactive with the grid. So just let's go back. Here you can see the results. Okay, we had a really small consumption, so we are advised to install 1 kilowatt and then a 4 kilowatt-hour battery. We have some numbers here, payback 5 years, for example, and you can see how the energy will flow in the whole system. Okay, so that's all for functionality number 1. We go back to functionality number 2, and the goal of this functionality is to calculate the flexibility that this prosumer or this local energy community can provide to the grid. Okay, here we have some forecasted data, which is the PV production, load consumption, and also energy prices. We have also some fixed and flexible assets that can help us to modify our consumption profile. Okay, we have, for example, dishwasher, which is the most suitable system to dispatch. Okay, because I can load it with dishes and then program it whenever the electricity is cheaper. And then I don't care if it's at the middle of the night that it finishes because there is no problem. We have also the washing machine and the dryer. Here it's a little bit trickier because we don't want our clothes to be for hours in the washing machine. And we have also the electric water heater that helps us to have domestic hot water or even heating in the house. Okay. So at the end, what we want to have is a operation strategy that maximizes the flexibility remuneration and minimizes the cost of the energy. Okay, so if we have this kind of energy consumption profile and we have a battery or we have an electric vehicle, we are going to store some energy. So we are going to consume more energy here when in the middle of the night where we were not consuming energy, in order to reduce our peak in the afternoon, in the evening, when the energy is more expensive. We have also the possibility to defer some consumption, like here we have a water tank, and what we are doing here is, instead of using this energy in the evening when everybody is taking a shower, for example, we are trying to schedule this consumption in other times, so we can avoid having this peak in the evening. Okay, so we can have a peak shaving strategy, or we can have also to reduce this consumption during peak time. At the end, what we have is a lot of inputs. We have PV power, which is consumed. We have some flexible loads. We have batteries and electric vehicles that act like batteries. And also we are depending on the energy and flexibility prices to buy and sell. This model is updated every hour. And at the end, we have an idea of the reduction of the cost of electricity, because we are able to allocate all this consumption to other times when the consumption is, the grid energy is cheaper. So here you can see the different plots that our tool is performing. Let's have a look on our input data. We have the PV production that is expected. We have a forecast here. Okay, it's a very sunny day. It's perfect. We have also some prices. Okay, you can see the cost of the energy when I buy it, and the income that I get if I sell it. It's always less. So normally we are trying to self-consume as much energy as we can, and we have a price. Okay, this would be the price that we pay for the energy in these 2 days if we don't take any action. Okay, but we have some expected power consumption. Again, this is a forecast, and here we can distinguish between the fixed load in blue. This is a low. This is some consumption that I cannot change. It's normal. Is my fridge, for example. I cannot just switch it on or switch it off. it's always on, and I cannot change it. But we have some other consumption, like for example the dishwasher, the washing machine, the dryer, the electric water heater, that are. This is the most convenient time for me. Whenever I need to use it, I'm going to use it. Okay, but let's have a look what happens if we try to modify this time. Okay, let's assume we don't have any battery, but we do have an electric vehicle, which is at home sometimes and not always, and I'm charging it whenever I'm ready. I'm also able to discharge if we have a vehicle to grid charger. I'm able to provide energy to my home if needed. Okay, so we have defined sometimes where the electric vehicle is not at home, so we cannot use it, but on the other times we are able to use the energy of the car. We have set some minimum and maximum variables. This is the state of charge that I want to have for my car when I leave home, and this is the expected state of charge that I will have when I reach home. Okay, here is the same, because we understand that the car is using this energy whenever it's riding, so we cannot take it's not like it was a battery. We also have the different grid power exchanges. This is, in other words, the money I pay to get my energy, and then we end up having a new distribution of the energy consumed of these flexible assets plus the contribution of the electric power of the electric car in coordinated with the maximal amount of PV power that we are able to consume. As you can see, we are not consuming everything because we are not able to store much more energy and we are not consuming at this time, but we are able to reschedule our loads in periods when are more convenient to us. At the end, we have a new cost of the electricity, which, as you can see here, is very reduced according to what we had at the beginning. Okay, so this is just for today. This is just an example. We are happy to perform a lot of simulations in the following months when all the validation cases will provide information, but we are very happy to see that this is possible. Okay, because this doesn't mean we need to invest a lot of money. This is just changing and rescheduling our loads. Okay, so now we jump in the two functionalities that are related to these DSOs, distribution system operators, and they are based on the previously explained digital twin. Here, what we want is to help distribution system operators to identify where they have problems and to propose the optimal location of batteries to improve grid stability with the minimum amount of devices or batteries. Okay, we will start from a grid model and a demand and generation forecast, and we will provide an optimal placement of these assets. So let's take, for example, this example. Okay, this might be a grid model provided by the DSO, or it can be generated by the digital twin, and we identify that the lines hanging from the secondary substation have some problems. Okay, for these 6 consumers, everything is okay. For these 2 and this line, we are close to have a problem, and then for these other 2, since they are gathering the consumption of everybody, we can have a line loading over 100. So what could be the solution here? To build a new line that is, of course, costs money and it takes a lot of time. So maybe this tool can help out here. So what we do is to perform some powerful flow calculations so we can have a grid diagnosis. We do this in medium and low voltage, and then we identify where this battery could solve our problems. What you see is this grid with problems that is anonymized because it's it goes together with the digital twin. So we are able to say, okay, in this feeder 3, for example, you should place a battery in T5, and this will solve all these problems. Because if you place it in T2, you won't be able to solve all the problems, just the one from this line. Okay, so this goes together with the next functionality. This one says, okay, place a battery in here, and functionality number 4 says how you should manage your battery to reach the highest possible efficiency. Okay, we are going to operate these controllable assets, and again we start from a grid model, and we have real-time power measurements data stream, and as you see, we have this problem here. We have already placed a battery, okay, but we provide an operation set points in order to control this battery and try to solve the problem. The flow diagram is similar to the previous one, but here we use real-time data and we optimize this real-time data calculation. Here we can see, which is more visual than the flow diagram, how this works. Okay, so first of all, we identify that the line loading, the loading of a line is experiencing some deviation. Okay, we forecast to have a problem in here, here, and here. This may cause a blackout. Okay, or we don't want to have people without electricity, so we have to tackle these problems before they even happen. So we make the simulation, we identify this, and then we are going to operate the battery in order it can help to solve this. Okay, at the end of the day, this loading is because there is a lot of consumption at one moment or a lot of generation. So if we have a buffer here, if we have a battery that can take energy or give energy, we may be able to solve this problem. So we set some set points to the battery to be charged or discharged, and what we manage is to reduce the loading of the line to the levels that are safe and that we avoid any kind of blackout here. Here you can see the modified line loading, and we have also what the battery is doing, charging or discharging at every time. Of course, if we are a lot of consumption, we have to discharge the battery, and after this, when the situation is restored, we will charge our battery to be ready for the next possible problem. So that's all from my side. Now my colleague Yanis from Third will explain the last functionality.
Hello everyone, thank you Luis. My name is Yanis. I'm working for CERT. And I'm going to present you, as Luis said, the last functionality of the DSS. Let me share my screen. Can anyone see my screen?
Yes, we can see it.
Thank you. And the full screen?
Yes.
Perfect. So functionality 5 of the DSS contains two services, Verify and Intema. Verify is a life cycle assessment service for energy community involving different sectors like building, storage, plant, transport, and public, assessing the environmental and economic footprint from construction phase to disposal or recycling. Intema, from the other hand, is an energy system simulation platform focused on a building level that provides energy-related metrics to non-expert users. Static input regarding building specification and location needed from Verify to define the life cycle inventory of the life cycle analysis of each technology and retrieve the country specific energy factors and emission factors. And from Intema to run the simulations and calculate the energy KPIs. Also for verify time series are crucial to estimate the use phase stage of the life cycle concept. And now in the next slide, after discussion with the validation case in the Data Cellar project, which took place, we made decisions to enhance users' accessibility for functionality 5 by simplifying the input and requirements for DSS users. And what I mean is that we had to deal with the most common problems we met. First problem was missing consumption and production data. It was hard to get energy data for building due to many cases, no smart meters and insufficient data resolution. For example, no hourly data or missing values. To address this, we use a simulation from Intema to estimate the required data. Another problem was missing detailed energy data. Before these input simplifications, using Verify required detailed energy data, like separate electricity profiles for appliances, lighting, heating or cooling. For example, if the building has an air condition, many users only had total electricity data, which made it hard to access. And to fix this, we made a disaggregation module that breaks down the overall electricity data into separate parts for heating, cooling, and lighting that contains an appliances also. This makes it easier for all users to and encourage people to use the service. The third was missing technology data. This data collected data on its technology aspects, such as embodied CO2, primary energy, and embodied primary energy. Capital and maintenance costs can be difficult in a community energy community level for the district. It may be easier for a specific building, but in the district level, it's difficult. So we solve this, which is compiles information from various studies. This means users no longer need to provide these details manually. And last was missing recent emission factors, which may not be available. So we use a model to predict the future CO2 factors for available data from and the following also slides from the AEM validation case. This local energy community has 8 buildings, 1 electric vehicle, 2 charging stations, and 1 transformer. To the design.
We are losing you, Yanni. I don't know why. Venzel. Luis, do you hear?
Yes. Yes, well, I see we are also having some kind of problems with Yanni's connectivity.
Okay.
Yeah, so I don't know. It seems that his screen is freezed. He was about to launch the simulation of the last functionality. I don't know. Maybe we can try to, if there is any question. Unfortunately, we cannot hear him. If we have any question for what I explained, maybe we can try to make it now, and we can give some time to Yanis to try to reconnect. Or
I'm sorry, I had the connection lost. I'm sorry.
Okay.
Yeah.
Okay.
Can you hear me now? I
Yeah, we
don't
can
know where.
hear.
Okay, perfect. I don't know where was the connection lost when.
Yanis, maybe you can explain this slide, and then you can launch the simulation.
Okay, perfect. Thank you. So let me minimize this. This is a demonstration that will show you in the backend how the service works using data from EAM validation case. The process is that we get the data through an Excel file, converted and pass them to the desirable JSON format to work the service, and we'll use it to perform the analysis. And let me show the demo in backend. And this is also disconnected. I will connect it again. So in the top right window, we can show here the JSON that we build from the Excel file with the validation case data. This JSON is going to be posted in our endpoint that starts the calculation of the two services, Intema and Verify. And we also, here we are going to see the response JSON. And in the bottom right window, we can see the terminal that the service is running. So after we post this, data from AM, we are going to see the service that is going to start. So, so here already running. We wait for Intema do the simulations, and an output response JSON with all the KPIs sent back to the top window, and this response file is going to be used by the dashboard to plot the results. Now I know this is very ugly. Always basket. Here we can see the calculations in the backend. And I know this is very ugly, always backend is ugly, but no worries, because dashboard is more beautiful when the service integrated. Here, as we see, we take the response. We can see it also here, how it will be. There is verify KPIs and Intema from all sectors of the validation case. And I had to mention there that all this calculation made on the fly. The dashboard will post the JSON, and we know we're going to save any of the data of the validation case. Let's continue there. Now, I mean, in the reality, how it will work on the dashboard. Each user logs into the dashboard, select functionality 5, inputs the required data via user interface, and clicks create project. Then the dashboard generates this file and automatically. And when the users initiate the analysis, the dashboard sends posts this JSON to our endpoint and displays the KPIs in graphs. Indicative graphs, you can imagine it would be like this. Here we can see the 8 buildings in the local energy community. Here is a operational CO2 emissions per square meters per building. This building, the elderly care home, this building, the elderly care home, is more. It's more energy consuming. It has a higher demand from other buildings, but we can see that it's more efficient, and also this building has a photovoltaic. In the right, we see how the income distributed through 2 charge stations. And here we can see the annual operating cost in the left, savings from energy save costs for the elderly care home. We can see how this decreasing through the years due to the photovoltaic degradation. In a year, in the middle of 2034, we can see that there is a replacement, so the savings are distributed. And in the right bar plot is the total cost of elderly care home, which is we can see significant cost increase in expense driven by major upgrades and replacements of the building technologies. And we can see that in the 20 and 34 years, also the peaks that it's due to the PV replacements. That's all.
Yanni, are you finished?
Yes.
Okay, thank you.
I thought that I had a lost connection again.
No, you are still here. Thank you very much, Luis and Yanis, for this very interesting presentation.
Thank you.
And yeah, you want to say some last words?
No, I'm finished. Thank you.
That's okay. Okay, thank you very much. I'm sure that what we have seen, and as you have already indicated, when we are with the dashboard, the mature dashboard, we are sure that this will be much more user-friendly and much more helpful for people to use. We have a few minutes in this period that we have for this presentation. I don't see any questions coming from the audience, from the participants, but I would like to indicate that, as you have already said, Luis, is that controllable access to achieve grid stability with minimum number of devices is a tool that you have developed in order to facilitate the process. And certainly is a basic benefit coming from effective use of flexibility, intelligently managed, I would say. Do you agree that this leads to substantial financial benefits to energy communities? And if you agree, can you elaborate a bit? How do you see this benefit coming back to energy communities, because we are targeting energy communities?
Yeah, exactly. The point is, energy communities are mainly gathering a lot of people, a lot of consumers. Okay, energy communities are a way in order to gather people, be more strong, and be a partner in the electricity system. Okay, single users are normally really small. We consume not so much energy, so we are not taking account. But if we organize in an energy community, we can be stronger. Okay. Being said that, energy communities, as well as being an aggregator of a lot of consumers, we have a lot of energy. Okay, a lot of energy and a lot of energy data, energy related data. This data nowadays is not being used. Okay, this data could be used in order to run these algorithms that can reduce the electricity bill, and in the future we could also use this energy data to understand our consumption, be able to say we will need in, let's say, for example, in 5 years we expect our consumption to be this high, and we will need a new line, or we will need to place a battery in here. So we can transform energy communities not only in consumers, but in service providers. So energy communities are starting to be an important actor in the electricity model, since they can modulate, they can store energy, they can provide information, and they can help planning on how the new electricity system will be. We cannot, of course, forget that they can trigger the development and the installation of PV systems, battery systems, or any kind of renewable generation systems. So for this reason, these kind of algorithms in combination with data spaces can bring the most of the non-exploited data of energy communities.
Yeah, thank you very much, Luis. And I think this is brings energy communities in the center of this energy management of tomorrow, of the energy transition. And DSOs, as we know, they are market facilitators, and hence highly interested in what you are developing. The DSS and digital twin services are very important for DSOs, and you quite rightly you have underlined that. And as I can see, it is a win-win situation between energy communities and DSOs for the first level optimization of the energy system, as we see it, for the benefit of energy communities. And I think quite rightly you have described it, and I'm sure that you have a lot to say. But if you want to say some last words on this, and then we can move on with the next speaker.
Yeah, I mean, just to point out what you mentioned, it's important to change our mind and to identify that the energy communities and consumers are now an important actor, and without them we cannot just forget them, because they are a very important part in the new. Could you hear the last things I said?
No, we didn't actually.
Okay,
the last sentence, huh?
Okay, it's just that, yeah, we have to put the energy communities in the center, and these kind of tools can help to close the bridge between technology, grid, and energy communities. So yeah, that's the important point.
Yeah, thank you very much, Luis and Yanis, for this very interesting, and we will be waiting for the mature dashboard to dive into your solutions. Thank you very much. And I think we can move, yeah, thank you. We can move on to Sarah De Luca, who is with us, and she will speak to us about artificial intelligence services for local energy communities. And the same, we will go through the presentations that Sarah has prepared, and then follow a couple of questions at the end to make your participation more interesting. So Sarah, the floor is yours.
Hello, good morning. Can you see the right screen, the one with the PowerPoint presentation? Or are you seeing the other?
We are in the background.
What about now?
Perfect.
Yes,
Okay.
now it's perfect.
Okay, thank you, Venizelos, for the introduction. I'm Sara De Luca. I'm from Links Foundation in Turin, and I am an AI researcher. Today, I will be presenting the services based on AI that we developed for the DATA CELLAR project. Okay, so let's start with an introduction on what is an AI system, an AI model, and specifically how it can be applied in the energy field. So the artificial intelligence models are computational algorithms that want to simulate the human brain, the human intelligence process. It learns from example data, so it basically learns from positive examples that we feed into it. The models can be applied in the energy field to several applications. Today we will see some of the ones that we implemented. For example, it can detect anomalous patterns in the energy consumption to signal if there is any alert, if there is any problem, or it can be used for predict when maintenance is required for an appliance based on the consumption profile. Just as an example. Let's go a little bit more in depth on how an artificial intelligence works. So first of all, there is the training phase. In the training phase, we feed the model, which at the beginning is just random parameters. We feed examples. So we give it an example input and what we expect to have in output. If we have enough training data, the model will be able to learn and generalize the concepts, and eventually it will be able to predict the task for which it was trained with a certain accuracy. So how does it work? At the beginning, the model predicts at random, but internally there is a loss function. The loss function is simply the difference between the predicted output and the true output, that the one that we would expect. And this loss function is basically the error of the model. This error is backpropagated, which means that it's sent back to the model so that the model can learn from past errors, basically. Let's see a little bit in a more schematic way how this works. So what we need to do is have what is an input data, so what we expect the model to receive as input, and what we expect the model to give us as output, so a correct sample output. We feed the input to the model, and as I was saying at the beginning, the model will give a result, but this result will be mostly random, a random calculation, because the model is not trained yet. So what we do is take the output of the model, compare it with the expected output that we have in our training data set. So what we know would be the correct answer. We compute the loss, so we compute the error that the model just made, and backpropagate the error to the AI model so that the model can update the parameters in order to tune the answer to what is the expected output. This process is repeated many times, as many as we have input data, until we get a model trained which is enough accurate. When we reach the desired accuracy, we can stop training. So how do we apply all of this in Data Cellar? The workflow with which a user can consume these services is the following. So a user has their own data that they have for their from their energy community or from their household or PV panel system. Through the connector which connects to the Data Cellar data space, the user accesses the dashboard, which is the global dashboard of the Data Cellar project, the same one where also the tools presented by my colleagues will be hosted. The dashboard will dispatch the request to the so-called deployment platform, which is, let's say, a tool that stores all the pre-trained AI models that we offer in Data Cellar. We'll retrieve from a weather data service information about the weather concerning the same time period and the same location as the input data of the user, and use it to generate an output using a pre-trained model. At this point, the deployment platform will send back the output to the dashboard, and the user will be able to see and utilize the output from these models. So what are the pre-trained models that we offer? First of all, let's start with the very simple forecasting of the production from the photovoltaic panels. Here, the only required input from the user will be some past examples of the production from the premises. How does it work? The model is already trained because we already trained the model with some past data and public data sets. For the utilization, what the user must provide is the past sample from the production of their PV panels and an approximate location. The approximate location is required because in this way the module can derive weather data. And in fact, the forecast model, the first thing that it does is retrieve the past weather data concerning the same time period as the past production data, and retrieve the future the forecast for the weather for the next 24 hours, in this case, 24 hours. And so the model will use the past examples from production and weather, and the weather forecast for the next 24 hours to generate an output about what is the expected production for the next 24 hours. Same thing holds for the forecasting of the household energy consumption. So if, for example, a user wants to predict the energy consumption for the next either 24 hours or even 1 week for, I don't know, schedule the energy usage in a more efficient way, or predict when it's peak time so that it can, I don't know, organize their consumption schedule. It can be useful to use this model. And also here works similarly to the forecast of the PV panel production. So what the user is required to have is past production data. So some examples of what is their energy profile what was their energy profile in the past, and also postal code or an approximate location so that we can derive weather data. These two inputs are given from the user to the forecast model. The forecast model will retrieve from the weather module the past weather data regarding the same time period as the past input data, and the 24-hour forecast, either 24 hours or 1 week, according to the desired output. And so the output will be a prediction based on the past profile of the future profile of consumption of the user. Another service that we have deployed on our deployment platform is the anomaly detection. The anomaly detection can be also here as the forecast applied either to production, PV production data, or consumption data. These two are two different models, but according to your needs, you can select what kind of output you need. So what is anomaly detection? Anomaly detection is the task of identifying unexpected patterns or deviations or spikes in the energy profile, both consumption or production. So this is really useful to understand and predict if there is some maintenance to do, or to optimize the lifespan of the appliances at which we apply the model. How does it work? Also here, what is required from the user is examples of the past either production or consumption data. So an example of their profile and an approximate location, as always, so that we can derive weather data. The anomaly detection model retrieves both the past weather data and the forecast for the next 24 hours. And what happens inside the anomaly detection model is the following. So first of all, we use the forecast model that I previously explained to generate the 24 hours prediction of the production or consumption or whatever there is in input. What it does is making a difference between the actual consumption or production, so the actual energy profile, and the predicted one. So at each time step, it will compute the difference between the predicted and the actual energy profile, and if the difference is above a certain threshold, then it means that there is an anomaly, and the system will raise an alert. Okay, one last example of our pre-trained model is the NILM, non-intrusive load monitoring. This model takes the energy consumption profile of a household, and it tries to spot the patterns that so to predict the features of each appliance of the house, to try to separate the profiles of the appliances without actually having to put a meter or a sensor on that appliance. So that's why it's called non-intrusive, because given the global energy profile of the household, the model can derive the profile of consumption of each appliance of the house. So that is why the only input required is the load profile of the household. How does it work? So here we have the aggregated load. We have one model for each appliance that we want to disaggregate. This means that for each appliance that is commonly present in a house, we trained a different AI model. So the same model trained with different training data. So each model is specific for an appliance. For example, if we have the aggregated load and we want to disaggregate the load for fridge, dishwasher, and washing machine, we need to use 3 different models, giving them the same aggregated input. And what we obtain in output is the load of the fridge, the load of the dishwasher. As you can see here, the fridge has a constant and periodic profile, while the dishwasher maybe has just some peak time and then it's always off. Same thing as the washing machine. Okay, and this was all for the pre-trained AI models, so the models that we make available for users only without requiring the user to do some training. But we also offer a platform, a tool that the user can access to develop and train their own AI model, their own service. So this platform is called Orange Data Mining. It's an open source library that allows for data visualization. It has inside a lot of state-of-the-art machine learning algorithms that are not difficult to use, data visualization and data pre and post-processing. It is a drag and drop interface, meaning that there is a panel with the widgets that you can take, drag, and drop inside the right sheet here to link each block, each operation with one another. And in fact, we have several kinds of possible interaction and functions that we can apply to the data. For example, we have the transforms, so the data processing operations that we can apply to our data set. The visualization services, so if we want to, I don't know, plot the distribution or have a bar plot, for example. Then we have, as I was mentioning, several types of different state-of-the-art AI models. These models require, of course, a little bit of domain knowledge, does not require programming skills, but of course, a user should know which kind of model is best for their application, because each model can be applied to different use cases. And it can be both supervised or unsupervised model. I will now make an example on how you can build your own AI model. Here I created a workflow on each widget and each operation that we can apply to an example dataset to create a forecast model. So let's suppose that a user has locally their dataset. It does not want to upload the dataset anywhere. So what they do is, instead of uploading the dataset through the Data CELLAR platform, it will build the model on the platform and then execute it on their data. So first of all, this is an example dataset. For example, we have a daily yield, a timestamp for each value of the yield, and several other variables like irradiation, temperature, etc. What we do, first of all, is apply some pre-processing to our data. For example, we can do date filtering. So if we have any missing date samples to our dataset, we just interpolate the samples between dates so that we never have missing dates. Or we can do feature selection, meaning that maybe not all the columns in our dataset are needed for our application. So I don't know, maybe we want to discard the irradiation, just an example, because we might not need it. And date filter and feature selection allow us to either integrate or remove columns or rows from our table. Then next thing that we do is start with the actual training of the model. First thing, we divide the dataset into training and test, meaning that when we divide the dataset into training and test, we use the training, which is usually the majority of the dataset, to train self-explanatory the AI model. And we use the test part to see how to see how the model behaves without having the correct answer in memory. So while with the training set, since of course we used the solution so the correct answer to update the model internal parameters, it is easy for the model to predict the right answer. Instead, we test the model on data sample that it has never seen during training. This way, we can check how the model would behave in a case where we don't have the correct answer, and calculate accuracy metrics. Okay, so then we select the model that we want to train. In this case, I selected a random forest. It's just one of the first prediction models that was developed. We give the training set to the random forest and do the process that I explained earlier about the backpropagation and loss computation. And in the end, what we obtain is a trained model to which we can give the training, the test set. At this point, by putting a widget about data visualization, for example, here a scatter plot, we are able to visualize our data set compared to the predicted data from the random forest, and visually compare the output of the model to our data set, so to the true case scenario. In this way, this was just an example of one of the possible application of the Orange tool that allows to build any possible AI models that we can think with our own data, without the need to share and make the data go through the data space environment. Finally, once this model is trained on the user dataset, the user can upload the trained model on the Data Cellar deployment platform, the same one where all the others pre-trained AI models, the ones that I presented earlier, are hosted. And this way, the user can share a trained model, a model that has learned from their data without sharing their own data. And that's it. I thought that maybe we could have a poll. I don't know if you want to present it, or I can launch it. Okay.
Please go ahead. Yeah.
Let's see. Okay. Are you able to see the poll?
Yes, you can see it.
Yeah. It's just a question to collect some feedback about what could be the most useful model, so that we can further develop other models based on your feedback. We might know where to focus the most for improvement and developing new things. I will just wait 1 minute or so to collect all the answer. Okay, so the percentage of voters is it stopped. So maybe I can collect responses. I don't know if I will be able to share the results. If I do close, are you able to see the answers? Otherwise, I will just read them out loud.
Yeah, we cannot see them.
Okay. Okay, just for your information, the most what the audience thinks is the most useful, the one that would be most needed is the forecasting of the energy profile of a household. Second one is the forecasting of the PV energy production. I think this is because they are very basic application, and with basic I don't mean easy. I mean they are applications that enable several other useful applications. So I can understand why they are the most required.
You have another one, Sarah?
Sorry?
Do you have another one question?
No, it was just this one.
Okay, thank you very much, Sarah, for this. And thank you for the results and the reaction of the participants. I don't see any other questions coming through our area of questions. I have two questions that are addressed to Luis, but before we go to Luis to see the reaction for these two questions, you have mentioned in the slide 8, Sarah, that there is a possibility, or there is the facility for scaling up for additional AI models, and in order to populate and cover other areas that because you have developed certain applications, but certainly there are a lot more out there, possibilities and capabilities required by energy communities or other applications. The important thing is, how do you see this deployment platform, the dashboard that we will provide, how this is facilitated? If someone wants to extend it, how will this be facilitated? If you just say a few more words or a description of how this can be done, because we know that there's going to be more requirements and more additions and much more extensive use of this deployment platform in the future. Yeah.
Okay. Yeah, I understand your question because, of course, there are so many applications that could be done with the same data, and so we cannot possibly train all the AI models to all the possible applications. But what we are doing right now is trying to implement the ones that might be more useful, that might be more popular, and any user can use the Orange data mining platform to, I don't know, maybe take the output of one of our model and build on top of that a specific application that they might require. And so this way, what we provide among the pre-trained AI models are the most basic applications. This way, a user that might want something more specific might use this tool to build their own model. Just to make an example, so a user wants to have a forecast only for their washing machine, not for the whole energy profile. So what they can do is use the pre-trained non-intrusive load monitoring to take their aggregated load and obtain the disaggregated load only for the washing machine, and then use the Orange platform, just as in the example that I made, in which we built a forecasting model. So use the output of the non-intrusive load monitoring, and so the profile only of the dishwasher, to build a forecasting model that forecasts the profile only of the dishwasher. This is just an example of how the pre-trained model might be expanded through the Orange platform.
Mm-hmm. Thank you, Sarah, for that. And there is a question coming through the question online. Is there a link, it says, where we can test or download existing models? I mean, the ones you have presented.
Yes, there is an API link for the deployment platform. However, it's not publicly available because in order to access the pre-trained model, a user needs to first access to the DATA CELLAR platform and then dispatch the request to the models through the dashboard. And so we are working on this link, on this connection right now. And so as soon as it will be deployed, we will make it publicly available.
So if someone is very, he wants for some application he wants, or just test, or just see a bit of it, can he communicate with you to get access to a model that you have?
Of course, I can leave my contacts in the chat.
Very good. This is very good. I think we are open to these applications. We are, as Data Cellar, sharing our outcomes, which is good. Luis, can you connect so that we can look at the two questions? Of course, Sarah, stay on board, because I don't know if any other question will come through until we finish with these presentations. And Luis, the questions, I don't know if you see them. Is it an output? Let me go from the beginning.
I cannot see the
How
question.
are the buildings demand time series? Do you read them?
Say it again, please.
How are the building demand time series generated? Is it from a data-driven model that uses historical data?
Okay, I couldn't hear last part of the question, but I understand that the question is addressing the last of functionalities about building energy systems. So maybe Yanis, would you like to answer?
Yeah. Yes, I think this has to do with Verify. The simulations which in Tema generate using a physics model, not AI driven.
Okay. Good. Any additions you want, Yannick? No?
No, we only use a physics model, which is use weathers and this. That's all. Okay,
good. So the next question, Luis, I think is for you, is that I have a question regarding the digital twins. The grid topology is an input, or is it an output of the digital twin? Furthermore, can it simulate faults on the grid?
Yeah, actually, the grid topology is an output of the digital twin. The idea of the digital twin is to allow users that don't have access to this information, that don't have access to the grid model itself, to build up a simplified grid model where they can test different situations. Okay, so at the very beginning, as you remember, we only have the energy meters of the consumers, and we get the power and the voltage. With this, we are able to build up the grid model, and then, of course, when we have this, we are able to simulate the different faults that can happen on the grid. We can simulate with time series energy profiles how the grid will be congested, and many other situations. So the digital twin is like the beginning of managing grids for those who don't have any access to have this grid model.
Thank you very much, Luis, for that. I don't see any other questions. So since we have completed the two presentations, the two sessions, I'm sure our participants have received all the information we have given them today. The presentations will be made available somehow for all the participants. We will agree later on with organizers to see how presentations can reach the participants to this webinar. And thank you very much again, Sarah and Luis and Yanis, for the very interesting presentations and tools that we are providing for energy communities to support them in their build-up of managing their own energy resources and managing their local energy needs effectively and efficiently. So now I would like to pass on to Martina Galuccio for some last remarks and lessons learned, the takeaways that we want from this today's webinar. Martina?
Hi everyone. Yeah, I think thank you Venizelos for conducting this workshop, and thank you everyone for participating and for being interested in what we are proposing within DATA CELLAR. I think there is not that much to say because everything has been already discussed. What I can say is that we should continue this collaboration. So if from the participant there is some interest in some specific tool, please do not hesitate to reach out to us, and we can also manage to see how we can propose our solution within your specific case. And that's all from my side, and thank you everyone for participating.
Thank you, Martina.
I think that at this point we can close this meeting. Thank you everyone for the participation.
Thank you. Have a nice day.
Thank you.
Bye.
Thank you. Bye-bye.
Thank you. Yes, bye-bye.